This is the fourth lesson in this course on fluid mechanics, and the topic is the medical applications of the concept of hydrostatic pressure. The learning objective is to be familiar with the locations in the body where pressure measurements are used to guide medical therapy. I'll also talk about how the principles of hydrostatic pressure reviewed in the last video can be used to measure some of the body's various pressures. So let's start with the various types of pressure in the body. Undoubtedly, the pressure you are most familiar with is the blood pressure, which is more specifically the pressure present in the large arteries. This pressure is the consequence of pulsatile blood flow, so therefore it is non-constant. When the heart squeezes during the systolic phase of the cardiac cycle, blood flows into and through the arteries rapidly and the pressure is relatively high. When the heart relaxes during the diastolic phase of the cardiac cycle, blood flow slows down and the pressure is relatively low. You've probably heard the normal blood pressure cited as 120/80. I put normal in quotations here because what's normal for one patient may not be normal for another. Also, in some circumstances, normal does not necessarily mean best, but I'll still use it as an example. So what do these numbers actually represent? The top larger number is the systolic blood pressure, which is the maximum blood pressure during the cycling of blood flow. The lower number is the diastolic blood pressure, which is the minimum blood pressure during the cycle. Blood pressure is usually checked with one of these devices. People, including doctors and nurses, usually call them blood pressure cuffs, though their technical name for those interested is a sphygmomanometer. That word just kind of looks intimidating. But sphygmomanometers measure blood pressure not in pascals, but in an interesting and somewhat archaic unit called millimeters of mercury, or mmHg for short. We'll come back to that unit in a minute. You may be wondering, in addition to the blood pressure, how many other kinds of pressure are routinely measured in the body? There are at least a dozen. They include various intracardiac pressures, various pulmonary pressures, intra-abdominal pressure, bladder pressure, which is typically used as a surrogate for intra-abdominal pressure, intracranial pressure, and finally intraocular pressure. Perhaps you've already realized that some of these aren't technically forms of hydrostatic pressure. After all, hydrostatic pressure is most commonly defined as the pressure present in a fluid at rest due to gravity. Blood, for example, is neither at rest, nor is its pressure the consequence of gravity. But the principles of hydrostatic pressure can still be applied at many of these locations. And although there is quite a diversity of locations in which pressure can be measured, and diversity in how they are measured, all of them are reported in one of two types of units. The first is the mmHg, or millimeters of mercury, mentioned a minute ago. The second is centimeters of water. These are called manometric units, and understanding them requires a brief review of the barometer. A barometer is a conceptually simple means to measure pressure. Imagine that we have a shallow tray into which is poured some mercury, which works well because it's very dense. Into this mercury is inserted a transparent tube, sealed on the top but open at the end that is beneath the surface of the liquid. Essential to the functioning of the barometer, the tube must start with a vacuum inside it. A vacuum has no particles moving within and thus has no intrinsic pressure. What will happen is the pressure in the atmosphere, which as per the fundamental principles of hydrostatic pressure reviewed in the last lesson, pushes against all surfaces at right angles, will thus push down on the mercury. However, since the vacuum is not pushing back on the liquid it's adjacent to, the liquid rises in the transparent column. The height of the column is proportional to the atmospheric pressure, defined by this equation, which hopefully looks familiar from the last video. Because of the vacuum, this pressure gradient is just atmospheric pressure. As a unit of pressure, 1 millimeters of mercury is the pressure needed to push a mercury column up 1 millimeter against gravity. Now, as any meteorologist knows, atmospheric pressure is not constant. We have low pressure systems that typically bring bad weather, and high pressure systems that typically bring good. However, these changes are relatively small, and for many real-world applications, they can be neglected. Therefore, what is known as standard atmospheric pressure is defined as a constant, that is 760 millimeters of mercury by definition. This means that given the mercury barometer shown here, if the tray is exposed to atmospheric pressure, the height of the column will be 760 millimeters. Although it's not used too much anymore, occasionally you may still see a unit called the torr. 1 millimeter of mercury is the same as 1 torr. Mercury works well when we are able to use an external device to measure pressure, like the blood pressure cuff. However, there are some applications of pressure in which the measurement utilizes a column of liquid from the patient, such as a column of blood or column of urine. So we need a new unit of measurement, and since blood and urine have densities close to water, we use the unit centimeters of water. In this circumstance, as water is much less dense than mercury, it will rise much higher in the column. An important and often unappreciated conversion is 1 centimeter of water equals 0.74 millimeters of mercury. If you're wondering where this comes from, it is the same ratio as the density of the two liquids, since that is the only variable aside from the outside pressure that determines the height of the fluid column. The central venous pressure, which is the pressure in the right atrium, is almost certainly the second most important and commonly measured pressure in the body after the blood pressure. It can be directly measured with a catheter in the right atrium of the heart, hooked up to a pressure transducer. Although that's the most accurate technique to measure it, it's invasive and requires special equipment. Luckily, there's an alternative. In the body, there exist the jugular veins, 2 internal jugular veins, and 2 external jugular veins. And while any of them can be used for this measurement, using the right internal jugular vein is most common. Let's draw in the jugular vein here, along with the location of the right atrium. Since the jugular vein has a direct connection to the right atrium, there is essentially an unbroken column of fluid from the right atrium up the jugular vein. By coincidence, the pressure in this column is just enough that its top, as observed by dilation of the jugular vein visible on bedside exam, is high enough to be just barely visible above the clavicle in normal patients, depending upon the angle the patient is at. In patients with unusually high pressure, it will be visibly elevated above this level, and in patients with unusually low pressure, it won't be visible at all. In other words, the maximum height of dilation within the jugular vein above the level of the right atrium corresponds to the central venous pressure in the right atrium. This is known as the jugular venous pressure, or more commonly JVP. You may wonder how one could know the height above the right atrium, but by another helpful coincidence, the right atrium happens to sit 5 centimeters below the sternal angle, irrespective of the position of the patient. For those not familiar with the sternal angle, it is a palpable prominence in the upper portion of the breastbone where it's joined with the second ribs. So when a patient is standing or sitting upright, the JVP may look relatively low in the neck compared to when the patient's lying down. However, as you hopefully can see from the diagram, the total vertical height should be the same. So the central venous pressure in centimeters of water equals the vertical height of the JVP above the sternal angle plus 5 centimeters. This central venous pressure is a key physiologic parameter that provides insight into whether a patient is dehydrated, in which JVP is unusually low, or in heart failure, in which JVP is unusually high. There's another interesting use of hydrostatics on the hospital wards that seems so basic as to be hard to believe it's still done. I mentioned briefly a minute ago that bladder pressure, which quantitatively is usually not of great interest in itself, can be used as a surrogate for intra-abdominal pressure, which can be elevated in a number of surgical catastrophes. The first and still most common way to measure bladder pressure is to take a Foley catheter, which is a commonly used tube inserted through the urethra into the bladder, usually to drain urine, and raise it up vertically. If there is urine present in the bladder, it will partly rise up the column, at which point sterile water or saline is poured into the top, further increasing the height of the column until it reaches the point where the hydrostatic pressure in the bladder from the column of fluid exceeds the intra-abdominal pressure. When this occurs, more liquid added does not increase the height of the column, but rather further distends the bladder. Since the bladder wall is highly compliant, and thus transmits pressure very easily, the height of the fluid column above the level of the bladder is approximately equal to the intra-abdominal pressure in centimeters of water. That's it for this lesson on some medical applications of hydrostatic pressure. The next lesson will cover the very closely related Pascal's law.